Friction is classified as a non-conservative force. Effectively, it's a force where you can't reharness the energy again, like in a spring or an elastic band. Other examples of non-conservative forces are the normal force as well as tension. With regards to friction calculations, you have to intuitively figure out which way friction is going. If I end up pushing the object towards the right, the force of friction will go to the left. If I push the object towards you, the force of friction will go in the opposite way. There's no mathematical formula to prove it, you just have to think about it intuitively. The third part is that surface area doesn't matter. It doesn't matter if I lay this DVD down flat or if I have this upright. In either case, the force of friction is the same in both setups. The reasoning behind that is that if I have this laid out in this setup right now, you'll notice that there's a greater amount of surface area. All right, so the normal forces are a lot smaller at each contact point. Meanwhile, if I hold this up vertically and I try pushing this, there's a smaller surface area, and the normal forces are a lot greater in that smaller contact point. So effectively, the surface area versus the pressure balance themselves out, and the surface area won't have an impact on your final answer. There are two different types of friction formulas, one for while the objects are in motion and while the objects are stationary relative to each other. While they're stationary relative to each other, there's more bonding between the two. In fact, friction is electromagnetic in nature. In other words, it's a relationship between the molecules of object A and object B. So if they stay stationary to each other, they have a chance to bond, and the overall friction is a lot greater. You've probably experienced this before if you've ever tried pushing a couch. All right. At first, you have to give it a huge heave before the couch starts to move. And if you let the couch stop at any moment in time, you have to put in greater effort and force to cause it to accelerate one more time. And we can see the outcome of this in these lookup tables. All right, there are geeks out there that spend their lives figuring this out. And yes, there's a YouTube link or a Google link that shows you all the tables. All right. I do want to emphasize just one interesting point, which is right over here. All right, and this is the generalized relationship between your car tires and the ground. And you'll notice that on dry days, the coefficient of friction is a lot greater than on wet and rainy days. And that's why your cars, the modern day cars, have something that's called ABS, or anti-lock braking system, where it's going to adjust itself constantly multiple times in a given second to change its realm from gliding friction or kinetic friction to static friction. And if you're wondering, well, why does that work out? Well, this is the best thing I have for a wheel, and here I have a ground. All right. So while the wheel is rolling, it's actually experiencing what type of friction, kinetic or static? Think about it. And the answer to this problem here is that it's static friction. All right. If I'm able to unravel this tape over here and lay it out on this entire book, which I don't want to vandalize, you'll notice that the tape will stick statically to each point on the book itself. All right, so each point of this wheel here is static relative to the ground. Meanwhile, if I try to do a Tokyo drift like this, you'll notice that the contact points of this wheel change relative to the surface area here. All right, so it's making new contact points with a new surface as I'm gliding. So this is kinetic friction, and this is static friction. All right, so that's why when your car slows down, you want it to constantly make contact with the ground as it approaches to a stop. On a wet and rainy day, if it ends up gliding like this, your coefficient of friction will decrease because now you're moving over to kinetic friction, and your car might spin out of control. And that's something that you don't want. Okay, so let's go through a mathematical example of friction. All right, in this case over here, we're going to take it that the object physically moves, and that's why you'll see a mu k. All right, so you're taking it that you're pushing this hard enough that it starts to accelerate. Before we move on, we always need to start off with an FBD, or a free body diagram. As a reminder, with free body diagrams, the vectors must always point away from the object, and you never draw the ground. Okay, so we can have force A and force B drawn out. That's fine and dandy. Okay, you can see that the arrows point away from the object, never towards. This is known as a system diagram. All right, meanwhile over here, we have a free body diagram. Other forces that we need to keep in mind is that gravity comes to play here. This is an object that does have mass, and the surface of the table will provide an upwards force, which is known as the normal force, or Fn. The last force you have to think of intuitively, as I said. Friction, the mathematical formula will never tell you which way it will go. But according to the setup over here, if you're pushing at an angle like so and downwards, you know that the object will likely move this way. All right. So this is, I guess, the direction of acceleration as well as the direction of your initial velocity. I think that's better. Okay, the direction of your initial velocity. It is moving this way. So the force of friction must oppose it going in the opposite direction. Okay, so that you have to intuitively figure out. Now that we're done drawing out our free body diagram, we can get started on our calculations. One thing to keep in mind is that the ground itself will always match dollar for dollar all the downward forces. So the greater the downward force, the greater the normal force. The lesser the downward force, the lesser the normal force, until the object starts floating up. Then you don't have a normal force anymore. All right. So in general, if you're wondering whether you should be solving for the x dimension first or the y dimension first, it's really solving for the dimension that doesn't have friction, right? Because unfortunately, with regards to friction, you have to incorporate your Fn in the formula. It doesn't matter if it's mu k or mu n, or sorry, mu s. All right. The normal force needs to be solved first. All right. So you're going to solve for the dimension that has the normal force. In this case over here, it's the y dimension. Okay, and with regards to the normal force, it's going to balance everything dollar for dollar such that your F net y will go to 0. Otherwise, the object will float into the air, or the ground's not strong enough and it's going to sink down into the ground. Okay, so with F net y going to 0, our equation can be rearranged like so. So we can take all these terms over here and bring them over to the other end where they become positive. Okay, so to solve for our normal force, we need to know the mass of the object and gravity. That's fine. The downward force by force B, but we also need to know the downward force of object A. What you see on the right hand side, this is a proper diagram of a free body diagram. You never show the components in a free body diagram. But to help us out in today's example, let's just cheat and just very lightly draw in what the components of FA are. Okay, so FA has a horizontal component and FA also has a vertical component. Right now we're focusing on FAY, so we're looking at the opposite side of 30 degrees. That's why it's nice to draw these lines out, because then you can figure out when to use adjacent and when to use opposite over hypotenuse. So when to use sine and when to use cosine. So in this case over here, we're going to multiply FA by the sine of 30 degrees. And we can crunch it out and we'll get to an answer. Now, before I move on, some students will say, hey, wait a second. Isn't this downwards here? Shouldn't that be a minus sign? And you are half correct, but here's the thing. When we're solving these problems, we can either solve them either as a scalar calculation or as a vector calculation. So if I rewind back and I decided to solve this as a vector calculation, I would have arrows on top. And by definition, F net is the sum of all forces, so technically there should be a plus sign here, here, and here. All right, so if you decide to solve it this way, then yes, when you sub it in, then you'll have downwards or a negative vector when you treat it as a scalar down below. All right, but we've already incorporated the minus sign over here. Okay, we don't want to accidentally double negate and become positive again, and that's why there's a positive over here, because the minus sign has already been factored in earlier in our calculations. That brings on another important thing that I forgot to mention. In your free body diagram, you may want to also include this. All right, a coordinate system, because a coordinate system will define to the reader what is positive and logically what will be the negative values. All right, so VBY was negative because it was facing downwards, and that's how we created that equation for F net y. Okay, all the upward forces subtract all the downward forces, net to 0. Okay, so that's our normal force. Now we can find out the force of friction, which in this case over here, just according to what was given here, it's equivalent to about 10% of our normal force. So 10% of 65 is 6.5 newtons. Now that we solved for our y dimension, which goes to 0, our force of friction, which has this value here, now we can finish off with the x dimension. All right, and in the F net x dimension, it's the horizontal component of FA that allows us to move in the positive direction, and the force of friction opposes it, and that's where the minus sign kicks in over here. All right, so you don't need to have a minus sign up here yet, the force of friction is just a net value. Another thing to keep in mind is that the force of friction is a maximum value. All right, because like for example, let's say that there was no forward force over here, okay, that it was equal to 0 newtons. Does that mean that the object will start accelerating backwards? And that's how ridiculous it'll get, okay? So if your FAX is less than the force of friction, it's either one of two things. Either A, it doesn't end up moving, or B, if it was moving, it is now decelerating. All right, so that's the two outcomes. And if it was decelerating, at some point, it'll eventually come to a rest. And then they'll make you wonder, well, why did we use mu k in the first place? All right. So let's just continue with these calculations here just to see what the outcome will be. We have our FAX, which is right over here, which is our 32 newtons times the cosine, as it's adjacent to 30 degrees. Okay, so 32 newtons times the cosine of 30, and we're going to subtract it from our frictional forces. And here we have an answer. It being positive means that the object does accelerate towards the right here. At what rate does it accelerate at? Well, we'll need to divide that by the mass. All right, if F net is equal to ma, which is the second law, that's the second of Newton's laws, then when we rearrange it, it will look like this, and we have our acceleration. And there you have it. Part B of today's lesson is what do we deal with, or how do we deal with inclines? All right. Here's an example of an object that's on a level surface, but if we tilt the surface, then other wacky things will happen. Okay. In this setup over here, the reason why the object remains stationary when the ground is nice and level at 0 degrees is because the normal force balances out with the force of gravity. However, if we tilt it like so, then we know logically and intuitively that the box will start gliding downwards. So let's figure out what rate of acceleration it will have while it glides downwards. One thing you'll notice is that I changed my coordinate system. In the previous coordinate system, it was up and down. It is far easier to deal with inclines with a coordinate system that is either in line with the ramp or perpendicular to the ramp. Okay? So this is the inline dimension, and this is the perpendicular dimension, and those are the symbols that we use for inline and perpendicular. As for the forces involved with this, there are 3 of them. The first one is gravity, and remember, gravity always points downwards. So gravity does have a component that is inline, and it has a component that is perpendicular, and we'll solve that afterwards. But the normal force is always going to have this perpendicular force. Okay, the normal force cannot have an inline component. After all, whenever you deal with a normal force, by definition, a normal is always orthogonal to a plane. All right, that's the definition of a normal, which you'll learn in algebra class. All right, so if this is a plane and this is a normal, no matter how I orient the plane, the normal force will always be 90 degrees to it. All right, so it's always going to be perpendicular to it, no matter what perspective that you're seeing this from. And intuitively, if the object glides downwards, the force of friction must go upwards, or up the ramp. And that's all we have for the free body diagram. You shouldn't be drawing anything else beyond this. However, as an aid, and as to something I've alluded earlier, gravity has 2 components here. There's a component of gravity which will match the normal force dollar for dollar, and whatever that's left over from the force of gravity, that's what allows objects to glide down the ramp. Okay, so please don't include those 2 vectors as a free body diagram. In fact, you shouldn't be drawing the ramp either. I think I have it animated out where, oh, I guess I didn't animate this properly. Oopsie daisy. All right, your free body diagram should look like that without the ramp. Okay, that's a standard free body diagram. Okay, but we'll include all these extra things just to help us solve the rest of this. One thing to keep in mind is that whatever angle that the ramp is in its incline, it coincidentally matches up to the angle right up here in this little magical triangle that we've created. Okay, and as a quick proof of why these 2 are the same, first off, let's just deal with complementary angles. All right, so the complementary angle of theta will be dot. What do I mean by that? I'm telling you that dot plus theta is equal to 90 degrees. Okay, and that's the little cheat that we'll use in solving the rest of this. Okay, because the next thing we're going to do is that we're going to use the Z pattern to prove that this point over here is equal to this point right over here. So whatever angle we have up here is the same as the angle over here. Next, just knowing that between FG perpendicular and FG in line, they are 90 degrees to each other. Well, didn't we just state that dot plus theta is equal to 90 degrees? So therefore, whatever mystery angle that is right over here, that's equal to theta. And that's a quick way just to prove that the angle incline is equal to the angle that we have inside our force of gravity triangle, right? To try to break down force of gravity into its components. Okay. Now, there are many different ways of solving these problems. You could deal with things after the fact, but often because you're doing the same process over and over again, it's actually a lot more efficient in breaking down the components right at the beginning. Okay, so we know that FG in line, which is the component over here, is equal to FG times the opposite of our hypotenuse, or the sine of theta. That will always be true. Okay, and we can do the calculations for that right now. FG is equal to mg, where if we're given the mass, we're given that we're doing this on Earth, and the angle of incline, we can find out what FG in line is. So this is the component of gravity that allows the object to accelerate down the ramp. Okay, but the force of friction will cause it not to accelerate as quickly, and as we know, force of friction can only be calculated if we solve the normal force first. Okay, and the normal force will compete with the force of gravity perpendicularly. So, over here, we'll compete with that. So that's why we need to also solve for FG perpendicular. Okay, and FG perpendicular will work out to FG, which is this vector down here, times the cosine of FG perpendicular, and that's why we have that formula there. Okay, that's why we have a cosine there. So 10 kilograms times 9.81 times the cosine of 25 degrees will give us our FG perpendicular. Now when we look at this diagram over here, even though I've butchered it up, you'll see that in the perpendicular dimension, there's only the normal force and the force of gravity perpendicular. And again, the normal force will always match dollar for dollar any upward or downward forces or perpendicular forces, so it'll net to a value of 0. Okay, so Fn will equal Fg perpendicular. Another way of stating it is that F net perpendicular is equal to our Fn, which is going upwards, subtract Fg perpendicular. And since F net is equal to 0, our Fn is equal to Fg perpendicular. Kind of cut to the chase here with my pre-recorded PowerPoint. That's all. But this is also another correct way of notating it. Okay, so our normal force will match Fg dollar for dollar. It won't always be the case because sometimes you'll be having an object going down the ramp and there's a weather balloon holding it up as well, and that makes it a bit more complicated. Or somebody who's pushing directly downwards, all right? So not inline, but vertically downwards as well. Okay, so you just have to look at the problem and solve for it super carefully. Okay, now that we have our normal force, we can find out the force of friction. If this is an object that's gliding on top of wax paper, typically that's the coefficient there. So 12% of 88 works out to around 11 newtons. Now we can finish off our inline dimension. Okay, so our F net inline is equal to whatever that allows it to accelerate downwards, which is Fg inline, subtract whatever that's slowing it down, which is the force of friction. All right, so we have our 41 newtons, subtract our 10 newtons, which gives us 31 newtons. To finish off this problem, you know that acceleration is equal to F net divided by mass. Remember that Fg perpendicular goes to 0, so we do not need to use the Pythagorean theorem. Yeah, we don't use the Pythagorean theorem in solving for the hypotenuse because one dimension is already 0. Okay, so it's just our F net inline divided by mass, and then you can solve the rest. One last example I want to share with you before we end off. Just due to a potential copyright infringement, I don't want to go through this entire episode, but it's a story about Peppa the pig where there was a school bus that was going up on a super snowy day. And you know, if you're a physics nerd, you probably stare at this episode and wonder, well, what kind of coefficient of friction do these tires need in order to be able to go all the way up here? One thing just to point out is that usually snow tires don't deal with just friction, it also deals with traction as well, and that's why it has all these grooves. All right, but we're not dealing with traction in this episode. We're just dealing with friction. Okay, so what coefficient of friction is needed on the tire to make this happen? So what I ended up doing is I did a whole screen capture of this, and you know that slope is equal to rise over run, and you can choose any 2 points on the line. So what I did was I did a one-to-one screen capture, and I drew in a rectangle where the vertices of the rectangle just touch 2 points on the slope of this snow hill. All right, and we find out that there are 111 pixels going this way and 174 pixels going up and down. Doesn't matter what unit it is. It could have been 174 meters versus 111 meters, or 174 inches versus 111 inches horizontally. All right, we're looking at ratios at the end of the day because the ratios will tell us everything else. For example, if we draw a triangle right over here, then we can find out the angle of this triangle. Right, we have the opposite, which is 174, and the adjacent of 111 pixels. And you can see that the pixels will cancel each other out when we try to do the tan inverse. All right, so if tan is equal to opposite over adjacent, then theta is equal to the tan inverse of the opposite of 174 pixels, inches, meters, feet. It doesn't matter because these two units will divide each other out, as we can see in our calculations. Okay, now since we're trying to solve this using forces, we should always start off with our free body diagram. All right, so we have this mass of a truck that we don't know what it is yet. That's why we're just going to leave it as a letter M. Force of gravity goes downwards. The normal force is jutted at an angle that's perpendicular to the incline. And the force of friction here is what's allowing us to go up the ramp. Keep that in mind. All right, we want the force of friction of the traction, the static friction of the tires to allow the bus to go up the hill. And that's all there is in the free body diagram, nothing else. Now we're going to draw in this tiny little triangle over here just to aid in our calculations because that really helps us out. As for the 57.5 degrees, I got that from doing the tan inverse of 174 over 111. Okay, again, that shouldn't be part of the free body diagram, so I'm just going to keep that as a sketch on the side just for our references in our calculations. Okay, we'll start off with our Fnet perpendicular. All right, so in this dimension first. So in this dimension, we have the normal force that is going in the positive direction, and we have Fg perpendicular, which is going opposite of it. So our Fnet perpendicular is equal to Fn minus Fg perpendicular, which will balance each other out at the end, as I've proven earlier. All right, so you can also state that Fn is equal to Fg perpendicular since Fnet perpendicular goes to 0 newtons. So our Fn is going to be equal to Fg perpendicular, which is Fg times the cosine of theta, or mg cosine of theta. Force of static friction is equal to mu s times Fn, so we can sub in. And we're kind of stuck right now. I mean, we can sub in for g and theta, but we don't know the mass or mu s or fs yet. All right, so we'll just keep this on pause for now. Instead, we'll work with the inline dimension, and hopefully we'll have two equations that we can just equate together. As for the inline, Fg inline allows the bus to accelerate, I guess, in the negative direction. I guess I should have done positive up because, no, we'll just stick with this for now. We'll just stick with this, okay? Because usually we like Fs to be a negative anyways, all right? So Fg inline is going downwards, and Fs is going against it. One thing to keep in mind is that this is static friction, so the wheels are making constant static contact with the ground, right? It's not gliding upwards like this, it's making static contact as we're going up the hill. Okay, so in other words, your Fnet inline will equal 0. Okay, so it really didn't matter if you assumed upwards as positive or downwards as positive, because at the end of the day, you're still going to prove that Fg inline must match up with Fs. Fg inline, as this is opposite of the side, that's why we'll multiply by the sine of theta, so Fg times sine of theta. And now we have an equation that looks like this. And you'll notice that the mass doesn't matter. The planet doesn't matter. All right. Instead, we'll have a much cleaner formula. It looks like this. Mu s is equal to sine of theta over the cosine of theta. And as I've proven in a previous episode, sine of theta over cosine of theta has the same meaning as tan of theta. All right, so if we do the tan of 57.5 degrees, then we can find out that the coefficient that's necessary to make this happen has to be well above 1. Okay, so that's the amount of friction that the tires must have in order for the coach to go all the way up the hill. One last thing I want to point out is that, yes, this is the mathematical proof of a much simpler formula. If you really think about it, by definition, tan of theta is equal to opposite over adjacent. So really, these numbers over here would have given us the answer right from the get-go. Okay, where instead of doing all these calculations, all we had to really do was divide 174 by 111, and there you go. There's the answer, super fast. In fact, you're going to use this super fast hack in a future lab that you'll be doing in a couple days from now. All right, so instead of doing all the calculations, you just know that you need to have the ramp's height and run. Okay, so the rise and run of the ramp, and then that will tell you the corresponding coefficient of static friction that's needed for some object just to stay stationary on the ramp. And that's all I have for you today. Make sure you go through your homework, check your answers with the answer key that's provided on the website. Link is available, I guess, on the first video, so 1.01. The link is available there because it may change over time, of the textbook along with its corresponding answer key. And I'll catch you in the next episode. Meow, will see you later.